So let's start off. Radio communication systems. Pretty intuitive. You have a transmitting station whose energy is transmitted through a transmission line to an antenna, which then radiates the radio frequency energy through some medium, and then received by a receive antenna that then couples that energy through the antenna into the transmission line and into your receiving station. Wave propagation. So the medium. This is the vehicle through which the wave travels from one point to the next. Propagation means movement through a medium. Just as the rays spread out from the bulb of a lamp or the beam from a flashlight, in this case, this flashlight represents a directional, focused nature of the light. The light in the lamp, where the radio's wave may spread out in all directions, would represent an omnidirectional antenna. So again, that just depends on how the antenna is constructed, whether or not it's omnidirectional or if it's a directional. But here's to show you it in terms of light. Components of the electromagnetic wave. This wave is the radio frequency energy that your system is radiating. So what does it consist of? You have an electric field or an E field, which results from the force of voltage, potential difference. Then a magnetic field, the H field, results from the flow of current. The E and H fields are at right angles to each other and determine the polarization of the wave, created whenever an electric current passes through a wire, which is what your radio is doing. Radio systems that have cross polarization greatly reduce signal power. The electromagnetic field is used to transfer energy as communications from point to point. An antenna is a propagation source of these electromagnetic waves. So let's look at the first type of polarization, known as vertical polarization. The polarization itself is determined by the E plane. So we have vertical antennas on either side of the system, and we see that vertical polarization is perpendicular to the Earth's surface. You mainly see vertical antennas in those vertical whip antennas on tops of vehicles. So then we have also horizontal polarization, in which the antennas are parallel to the Earth's surface. And you mainly see those if you're looking at tops of homes that may have TV antennas. Those are horizontally polarized. Or more specifically, those antennas are called Yagi-Uda antennas, and those are ones that ham radio operators especially use for their operations on HF to direct the energy into a particular direction. Now, what happens if we have a vertically polarized transmitting antenna, like you see on the top left, but then received by a horizontally polarized receiving antenna? Well, what you're going to have is almost minimal coupling of the E plane, the electric lines of force, by that receiving antenna, in which case you will barely get any signal. So it's absolutely imperative that on both ends of your radio system that you're keeping and maintaining the same polarization of antennas. Propagation paths. We can have a direct wave, which it travels directly from the transmitting antenna to the receiving antenna. We see this mainly in line of sight antennas. It's limited by the distance to the horizon or line of sight. With that said, the antenna height and curvature of the Earth are also limiting factors. Radio horizon, which is actually a thing, is about 80% greater than the line of sight because of diffraction effects. In fact, the wave front, as it moves towards the edge of that horizon, will end up bending the front of that wave down and around, if you want to call it that, over the curvature of the Earth, but just for a little bit longer before it attenuates to the point where there's almost no signal left. Surface wave reaches the receiving site by traveling along the surface of the ground. A surface wave follows the contours of the Earth due to diffraction. Terrain affects propagation, so let's take a look at that. Salt water has very good connectivity, all the way down to jungle, very poor. And you're like, oh wow, jungle has a really moist environment with lots of vegetation, but it's because of that that causes these direct waves to attenuate heavily. And you know this if you've ever been in the woods, not just the jungle, but just any woods, and you're trying to transmit, let's say on your VHF Singar's radio, you're not going that far. Why? Those radio waves are getting heavily attenuated, absorbed by the trees. So something to think about. Ground reflected wave. When they're reflected from the Earth's surface, the reflected wave undergoes a phase reversal of 180 degrees. And we're going to talk about this because this can have and result in fading due to destructive interference between having one signal that comes in, as you see there, a direct wave in phase, and then you've got this ground reflected wave going in a phase reversal. And once those two signals match up at the receiver, they can actually either help each other or actually destruct the signal to the point where the receiving antenna gets a deep fade. More on ground wave propagation. So again, with the antenna, with ground wave propagation, increased antenna height increases distance. Vertical polarization is best for ground wave propagation. If you increase transmitter power, it can increase distance, but not proportionately that you think about. Meaning that if you are operating 20 watts, that gets you about 5 miles. That if you have a 2 times increase in power, that's going to get you a 2 times increase in distance. That's not the case, so you just need to understand that. Better ground connectivity increases distance. There's less noise during daytime. There's less bandwidth, leads to increased distance of your signal. Meaning if you use a modulation scheme that uses less bandwidth to operate on, then you can potentially get a increase in distance. So best way to describe this, if you know Morse code, very minimal bandwidth versus using your voice to communicate with. That takes a lot more bandwidth to get that message across, that Morse code will go and travel a further distance. Obstacles such as intervening trees will decrease distance. Skywave propagation. This is the bread and butter of HF communications right here. Skywave propagation is refraction of a radio wave by ionosphere, and that is the sole property of skywave right there. And that's what allows you to achieve long and intermediate range. So let's look at the layers of the atmosphere. A little quick lesson, if you did not know this, here you go. So the Earth's atmosphere is divided into 3 separate regions or layers. They are the troposphere, the stratosphere, and the ionosphere. The layers of the atmosphere are illustrated in this figure, 2-10. The troposphere is the portion of the Earth's atmosphere that extends from the surface of the Earth to a height of about 6 kilometers at the North Pole or the South Pole, and about 18 kilometers at the equator. Virtually all weather phenomena take place in the troposphere. The temperature in this region decreases rapidly with altitude and when clouds form, and there may be much turbulence because of variations in temperature, density, and pressure. These conditions have great effect on the propagation of radio waves. The stratosphere is located between the troposphere and the ionosphere. The temperature throughout this region is considered to be almost constant, and there is little water vapor present. The stratosphere has relatively little effect on radio waves because it is a relatively calm region with little or no temperature changes. And finally, the ionosphere extends upward from about 50 kilometers to a height of about 400 kilometers. It contains 4 cloud-like layers of electrically charged ions, which enable radio waves to be propagated to great distances around the Earth. This is the most important region of the atmosphere for long-distance point-to-point communications. And as a fun fact, the International Space Station has an orbit height of about 225 miles, so it's at the very upper end of the ionosphere in low Earth orbit. So let's look more specifically at the regions of the ionosphere, because this is where all the HF magic happens. So we have 4 layers, and we'll start off with the D layer, which is the closest to the Earth's surface. D layer ranges from about 30 to 55 miles. The ionization in the D layer is low because it is the lowest region of the ionosphere. This layer has the ability to refract signals of low frequencies. High frequencies pass right through it and are attenuated. After sunset, the D layer disappears because of the rapid recombination of ions. The next layer up, the E layer, limits are from about 55 to 85 miles. This layer is also known as the Kennelly Heaviside layer because these 2 men were the first to propose its existence. The rate of ionic recombination in this layer is rather rapid after sunset, and the layer is almost gone by midnight. This layer has the ability to refract signals as high as 20 megahertz. For this reason, it is valuable for communications in ranges of up to 1,500 miles. The F layer exists from about 85 to 250 miles. During the daylight hours, the F layer separates into two layers, the F1 and F2 layers. The ionization level in these layers is quite high and varies widely during the day. At noon, this portion of the atmosphere is closest to the sun, and the degree of ionization is maximum. Because the atmosphere is rarefied at these heights, recombination occurs slowly after sunset. Therefore, a fairly constant ionized layer is always present, both day and night. The F layer are also responsible for high-frequency, long-distance transmission. Now let's talk about propagation, hops, and skip zones. So you have a transmitting station in San Francisco, which has both ground wave propagation going out to some point, and then, depending on takeoff angles of the signal, can either skip out of the ionosphere or be able to reach another point. Let's say it skips completely over Denver for that particular frequency, and then another skip happens off to Chicago, and so on and so forth. The thing is that there is actually no skip zone as long as you have the proper antenna and frequency selected. You're the actual person that's causing the skip zone because you're on a particular frequency that so happens to have to skip over that city or that area. And so we can get it so that you can get a almost near vertical incident takeoff angle that allows the communication to, let's say, go out up to Denver from San Francisco. That's actually kind of a stretch, but let's just go with it. And you could have the ground waves take care out to a certain point, and then the signal come back down on, let's say, Denver, in which case you would eliminate a skip zone. There can be instances in which you have destructive interference or fading because the signal, by sending it so high directly up and coming almost back down, particularly in the same regions where your ground waves are propagating out to, that they can mix with each other and destruct. And we'll talk about that in another slide. How do you mitigate that? Well, you can use special NVIS antennas to hopefully mitigate that issue. Atmospheric propagation, we're going to talk about reflection, refraction, diffraction, and then finally absorption. So, reflection. Reflection for HF signals happens at the Earth's surface. Radio waves may be reflected from substances or objects they encounter during travel between the transmitting and receiving sites. In particular, it can cause phase shift between direct wave and the reflective wave, resulting in distortion or cancellation. We talked about that in the earlier slide. And then the amount of reflection depends on the reflecting material. Is it coming in contact with the ground? Is it coming in contact with a desert? Is it coming in contact with an ocean or a fresh body water? So let's look at this. We have here a light. Let's just say it's a laser to make this easier. And you're shining that laser at a reflecting surface. Let's say a mirror. Well, we have the angle of incidence. That is the angle from the, let's say, the laser to this line, which is called the normal or perpendicular line to the reflecting surface. Once it reflects off of that reflecting surface, it's going to come back out on the other side and at an angle that is actually equal to the angle of incidence. This angle is known as the angle of reflection, to which then there's somebody on the other side that would see that. So when you have a radio frequency wave, an electromagnetic wave, reflecting off of a surface, this is the same thing that will happen. Refraction. So this is the phenomenon that causes the bending of the radio wave when it passes from one medium to another medium of different densities. And you could probably guess what is this medium that's going to have a different density, and that is the layers of the ionosphere. They have different densities. So a wave passing through the atmosphere at constant speed enters a dense layer of charged ions, which would be one of those layers in the ionosphere, which causes refraction or bending. Diffraction. This is a phenomenon where a radio wave bends around the edge of a solid object. So most commonly we would see a mountain and you would have a transmitter. And the wave front will either get absorbed into the mountain or just above it the wavefront will actually slightly bend over it. And if everybody's ever taken a laser pointer and pointed it right at a very sharp edge, you will notice this effect, the effect of diffraction, where it will slightly bend over the top, and you'll notice that part of that laser beam will be slightly diffracted downwards from where you would expect it to hit. So try that sometime. But the same thing with radio waves. In fact, with VHF communications, if you have a mountain in between you and the other person you're trying to speak with, you could actually bend back that antenna, that vertical polarized antenna, back from the mountain, and the wavefront will be aimed at such a manner to which you could potentially get diffraction to help get that signal back down the other side to speak with somebody on the opposite end of the mountain. Try it sometime. Waves traveling in straight lines bend around these obstacles. So the energy is weak, though detectable, unless you're in the complete shadow zone. So this concept explains why radio waves can be heard behind tall mountains or buildings that are normally considered to block line-of-sight transmissions. Fading. Variety of factors. So we have absorption fading, where let's say there's increased absorption in the D layer, builds up during the morning hours. Or we're going to talk a little bit later about solar flares, where the D layer gets heavily ionized and also absorbs almost all signals. We have multipath fading. I alluded to this earlier, where you would have either a direct wave and then a ground reflected wave where the signal is out of phase by 180 degrees, in which when they recombine, they can potentially cancel each other out. That's multipath fading. And then you can also have selective fading as well, where you have two different paths to get there at almost two different times, and then that can cause some issues in the receiver. So what is NVIS? Is it a mode that you set in your radio? Can it only be used by amateur radio operators? Well, let's just talk about it real quick here. It's a form of HF propagation, which depends on the correct type of antenna and frequencies to allow you to get as high takeoff angle as possible of your radio frequency energy to reach the ionosphere and refract off the ionosphere to return back to Earth as close as possible. So what kind of uses? If you have mountains in the way that block line of sight VHF, UHF communications, and something that people do not necessarily consider is, let's say you're in Alaska and you have a mountain range that is blocking your SATCOM line of sight between your satellite antenna to the actual satellite that's located somewhere near the equator. It's actually a very low angle that you have to set your antenna in order to reach it, and that may mean going through a mountain, which obviously you can't do. So how would you communicate between some drop zone in northern Alaska to somewhere much further south? And that might be the case. Then you can use HF radio set up in NVIS. How far out can you reach? Well, actually, it's somewhere between 300 and 500 miles. In fact, in the next slide, I'll show you the comparison between NVIS, in which there is not necessarily a skip zone that reaches only out a certain distance, and then what most people do day in and day out, which is just a long distance contact with a skip zone involved. This is important to understand fundamentally, because a lot of people think they can just get a spread of frequencies throughout the HF band and they call it good. They have enough frequencies for quote unquote during the day. They have another set of frequencies they think will work during the night, and they may not realize they were not assigned frequencies low enough to allow them to communicate during the evening. So we look here between 1.6 and 30 megahertz. Some people say only 2 to 30 megahertz is the quote-unquote HF band. But then we actually see NVIS occurring around 1.6 to 12 megahertz. I want to emphasize that it's just based on the atmospherics and the solar conditions. Just depending what's going on, if there is a much higher sunspot count, which by the way, we are at a complete lull right now, maybe up to about 4 for our sunspot number count. But if you get anywhere, we're talking about we're at the peak of this, we're getting like 100, 190, you could, during the day, get as high as 12 megahertz for your upper limit frequency to utilize NVIS. The best way to think about NVIS is take a water hose, full pressure, and point it straight up. And then what you're going to get is this umbrella effect. It goes up, it culminates, and then it comes and drops back down. Some of it right back on you, and some of it some certain distance away. The image you see here, figure M-1, taken right out of Army Doctrine, shows the red dot, let's say that is your transmitter, and you see the signal does not just exit out at a single angle. It encompasses many different angles, and it will reach anywhere between 90 50 degrees and then subsequently refract off the ionosphere and come back down. Now you see where in case of this image it says the F1 layers where everything's refracting off of. That depends on the time of the day. At night, just what you've learned off of my previous video in episode 1 on RF theory, at night F1, F2 layers combine to just the F layer. The E layer goes away, and definitely the D layer is completely out of the question at that point. But during the day, the D layer has a lot of absorption effects, and we actually have to go higher in frequency during the day, lower in frequency at the night. The NVIS rule of thumb is nighttime you're looking anywhere between 1.8 and 4.9 megahertz to still operate in that same 300 to 500 mile footprint. And during the day, you may have to actually move up to around 5 to 8 megahertz, maybe even as high as 12 megahertz, again, depending on sunspot count and some other atmospheric condition that might happen. So let's start off with your basic horizontal dipole antenna. The antenna itself is a length of wire, or actually two wires that together is a half wavelength of the intended frequency you're using. So to go back on wavelength, which we typically refer to in meters, such as 80 meters, 40 meters, is actually describing a frequency, but with respect to its wavelength. And we have a calculation you can use in order to find the length in feet. So you take 468 divided by the frequency you intend to use, or that is center to a group of frequencies you intend to use, in megahertz. So let's say that you want to use frequencies around 5 megahertz. You would take 468 divided by 5, and you get roughly 90 feet. It's almost more like 94. And then you would take half of that to come up with the quarter wavelength of wire that you would have on each side of this device called a balun. So what is a balun? Why do you see that up there? Well, balun means balanced to unbalanced. And the reason why we have this is because most radios on the back of them have this connector that is meant to hook to a coax line. Well, the coax line is formed with a center signal wire surrounded by this shield, this metal braid. Well, the braid itself doesn't have the signal on it, but the center wire does. The whole point of the braid is to actually shield the center signal wire from electromagnetic interference. Having said that, though, both wires, if you want to treat them as individual wires, do not have equal amounts of that signal on them. And so we use this balun to then convert that center signal wire and the outer ground braid to then have a signal go across both wires, to the left of that quarter wavelength of wire and to the right side as well. At the very ends of these wires, you need to use an insulator, a dielectric. So that can be plastic, that can be glass. They make them. You can buy them online, or if you're in a pinch, you're out in the field environment, you can put a hole through a plastic spoon that comes with your MRE, and you can utilize the properties, the dielectric properties of a plastic spoon to act as your insulator. The reason being is once everything gets wet in the rain, you want something that can ensure that the signal stops at the end of the wire and doesn't keep going. And then you can use whatever type of rope you need to secure it to tree. So, having said that, that means you have to have objects out there in the field that can support this wire antenna. You can either use two OE254 support pole systems, or you can try to find nearby trees. Ensure, though, that when you're using these dipole antennas that you're not deep in the thick of a forest. You can to some extent, but you want to try to find somewhat of an opening or clearing, because the trees will tend to absorb some of the signal, and it's best to try to get an open area as best as you can. Though I've operated one of these in the middle of a forest and get somewhat good performance. Bottom left hand of this screen is the GRA 50 balun. This is a typical military balun that you'll find out there. You can see in the center of it is where you would connect in the coax line. They're typically N-type connectors. This is something that we don't typically use in the HF frequencies in amateur radio. We typically use SO 259s and or also known as UHF connectors, but not N-type. That's more of a professional grade connector. It helps seal out moisture better. So when you go online looking for coax line with pre-soldered connectors in the amateur radio world, you're going to notice that that will not connect with some of the military gear we have. So you just have to be mindful of that. You have to ensure you know what you're ordering with pre-soldered ends that will match what you're using. We also use BNC heavily in the military world as well. So you just have to be mindful of that. Bottom right-hand corner of this chart is the radiation pattern. And it's interesting to note that as you're looking in from the side of the antenna, the ends of it, if you will, looking down the wire, if you will, is the radiation pattern in which a lot more of the energy at lower frequencies is directed up. And this is fantastic for near vertical incident skywave because we're typically using 2 to 12 megahertz, and you want your antenna to radiate with a high takeoff angle as possible. What you see at 10 megahertz and higher is that the antenna will then radiate more signal at lower angles. Think about that. So one of the reasons why NVIS is found at lower frequencies is due to this as well. But with this antenna, you can utilize NVIS and you'll be good to go. With your radio, you see the orange box there, the dark gold PRC 150 radio. You want to make sure that that radio is grounded. There is a grounding terminal on it. You want to ensure that you stake that into the ground. It works as a counterpoise and helps boost performance of your radio. So always ground it, no matter where it's located. How can we improve the antenna's ability to gain a higher takeoff angle? How can we improve NVIS performance? Well, this works. Let me show you here for a second. You're going to have your normal horizontal dipole antenna that's half a wavelength long. So again, if it's 5 megahertz, about around 90 feet long. Okay, you'll have your insulators here, your dielectrics, and then rope tied to either a tree or a pole out in the field. About 0.15-ish wavelengths below the main dipole antenna, you just have a straight piece of wire. Again, using insulators to ensure that it is isolated from whatever support structure you're tying it to. The length of it will be about 5% longer than the dipole's length. This is going to act as a reflector. For some of you that are ham savvy and antenna savvy will note that this is what is basically the foundations of a Yagi-Uda antenna. You have a reflector, a non-driven element that is slightly longer than the driven element, meaning this is where your coax cable is connected to. and this helps to direct the energy, in this case vertical, and this will help us achieve a higher takeoff angle. It will direct more of that energy as high as possible instead of having some of that energy radiating towards the sides. And this does work. I've had one unit that did see an increase in performance using this. So this is one method you can use to help boost your performance. Notice though that again, this is at the halt. So something that you might use at a tactical operations center, but not something you're necessarily going to set up that quickly when you're on the move, because you can't, you're on the move. Next, we're going to talk about the inverted V. This has different characteristics. I typically use inverted V antennas not so much for NVIS, but more for gaining directionality, higher frequencies, longer distance contacts. But just like with the dipole, horizontal dipole antenna, with this inverted V, you can place a reflector below the driven element, the main dipole antenna that you have your coax connected to, and you can then again achieve a higher takeoff angle, directing more of your energy vertically to achieve better performance on NVIS. You can use this as well. Why would somebody use an inverted V rather than the horizontal dipole? Well, let me take you back to the previous slide here if I can, and you're going to notice you need two support structures. What if you can't find or you don't have two support structures? Well then, if you only have one single support structure, you just tie the balun to that, say this a mast or just a tree, and then you can use stakes to secure the ropes connected to the insulator, the ends of the antenna. So it really means that you can still achieve the mission, just given restrictions in the environment. Off-center fed dipoles. I'm going to talk about this one because I see people trying to present this to soldiers as another option of an antenna you can get. And there's amateur radio companies that sell these, but they're actually meant to be used with amateur radio frequencies. So what it is by offsetting where the balun is located with respect to the rest of the antenna, then you can achieve better standing wave ratio performance at key frequencies. And you're going to see here it says it will have natural dips in the SWR throughout a frequency range due to have reasonable low impedances at even harmonics. Let me break that one down for you. So you typically want an antenna with a 2-to-1 SWR or better, 1-to-1 being the ideal. It's hard to achieve that perfectly. There's always imperfections in the system, but that's what you want. What that means is that for every watt that you're transmitting from the radio, it's actually going out of the antenna. When you have a mismatch, an SWR mismatch, some of that energy is reflected. I'm not going to get into the weeds on that in this lesson, but what it just means is that you need to have a well-tuned antenna, and for anything that you're operating on that is not tuned very well, the PRC 150 and other higher-end amateur radios include a tuner, a built-in tuner that will tune it. Okay, PRC 150 will tune garbage. However, let's say you have a 7-to-1 mismatch going on your antenna. PRC 150 may tune it, but then your antenna and your performance will not be as efficient as if the antenna already was tuned maybe down to at least a 2-to-1 or better. And then the PRC 150 would ensure to try to get it to a 1-to-1 or 1.1-to-1 match as possible. The off-center fed dipole solves the issue of being able to use a range of frequencies across the HF band, 3 to 30 megahertz, by having those natural dips, those 2-to-1 or better SWR performances at those critical frequencies that we use. Problem is, the military doesn't use amateur radio frequencies, and so if you're trying to inform soldiers about, hey, there's an off-center fed dipole you can go out and get, well, the SWR dips are actually at, let's say, 3.5, 7, 14, 18, 24.8, and 28 megahertz. Those are popular amateur radio bands. The problem is the actual military frequencies that you're using, if you use this antenna with them, the SWR is actually 7 to 1. And so now the PRC 150 is trying to tune that, and it may in the end successfully tune it, but now your overall system performance, the max amount of power that you're actually able to put through that antenna now is reduced, because now you're trying to tie that all up in the tuning circuitry, and it just doesn't work as well. So the reason why I'm going in depth and ad nauseum about this is that this is not necessarily the best solution for a military problem. Definitely a great antenna for amateur radio, though. The terminated folded dipole. Now this is a fantastic antenna if you have the space for it. It is 90 feet long. They typically always sell these in about that length. That happens to be half wavelength of 5 megahertz, which is about the middle range of the NVIS slate of frequencies. It almost kind of looks like two dipole antennas stacked on each other, and it almost is, but it's actually one contiguous wire that runs out, around, and then back over in a big loop, and then back over again. Each of these white vertical lines actually is, and what they use for these is nothing more than PVC pipe with a hole cut through them to put the wire through, and they're just spacers. At the very end, a rope goes through the very last section of PVC pipe on each end, and then you tie that off to an insulator and then to another rope that then goes to your anchor points. United States Military Academy utilizes one of these. Fantastic antenna. And we have used this to talk all the way into Europe and subsequently all the way over to Vancouver. So you can get really good performance from just a basic dipole antenna, no Yagis needed, as you need. The fantastic thing about this antenna is that it's what's known as broadbanded. That means that pretty much, okay, I can't stake my career on this one, but pretty much gets a 2 to 1 SWR or better across all frequencies 2 to 30 megahertz. That's not necessarily true. I've had some touchy points with some certain frequencies that did require the use of an antenna tuner. But the good news is that all these military radios have built-in antenna tuners. Again, make sure that your radio is grounded, whether it's inside a building that needs to be grounded to a ground point, or if it's outside, stake that into the ground to its grounding terminal. These can run you, depending on what version you get, either like a 100-watt version, or if you get the high-powered version, depending if you're hooking this up to a power amplifier, it might be doing more than 800 watts, you're looking at anywhere between $300 and about $700. Considering how much military antennas are sold, that's still a pretty good price. And you can go online and find these. So this concept, if you're using amateur radio, I have shown you in previous episodes, and by the way, even military HF radio, that if you're trying to talk to a certain station a certain distance away, that your ability to speak with them throughout the day on that one frequency may change, such that maybe at night you're able to speak to them on a lower frequency, but during the day, heavy fading occurs on that frequency. The sun comes up, the D layer starts to energize back up and absorbs certain frequencies. You need to move higher in frequency in order to speak to that same station, just as an example. Well, the problem is, how do you each hundreds of miles away using nothing else, and let's just assume that we're really using this the way HF should be used, and that is all other communications are down. how do you all agree upon moving to another frequency? There's all kinds of HF frequencies, and how do you move to another one higher up? How do you agree upon that? Because you may not get that word out at that time that the sun's coming up, and what you were just talking on now is no longer usable. How are you now going to communicate to go to another frequency? So automatic link establishment depends upon a priori knowledge of what frequencies we're going to move to throughout the day, and ensure that those frequencies are in fact going to support that link. If you could program all those frequencies into your radio, and then have a way for your radio to scan through those frequencies and send a short burst of data, and then the other radio picks that up and then can provide word back to the other one, the other radio, of the quality of the signal, link quality analysis, then the radio can make what's called soundings on every frequency, and it just says, hey, are you there? Hey, are you there? The other radio answers back when it does hear that call and respond back with the bit error rate of that short data burst back to the calling radio. And now the radio has knowledge for that specific sounding time. Where is the best frequency? What is the best frequency to communicate on? And this is huge, and it required digital signal processing. It required these more advanced radios that were starting to come out in the late 70s, early 80s. This is not a feature you would have found early 70s and older. And since then, it's extremely popular because it allows folks to just select what station, because each station gets a call sign, channel, an address ID, if you will, and you just select that. And at that time, the radio is going to go through and again do an update of the soundings and figure out what frequency is the best to communicate to the other station on. Again, depends completely on the fact that you did a good enough job on getting enough frequencies low enough to high enough to support throughout all 24 hours of the day. And this is just something that spectrum managers need to understand, that when you do that, remember I talked about vocap analysis, that ahead of time you do the homework and finding out, do we have all the frequencies available? So let's move on. So after the ALE system, this HF radio, and again, it could be a HF radio with this built-in, or you have a computer that's doing all of this ALE functionality and merely communicating through a radio. It could be just a normal average amateur radio. I'll show you a slide later on here in the presentation that shows that software you can use for yourself if you're an amateur radio operator. Let's go through the history. So in the 70s and early 1980s, we had early automatic link establishment systems. Few companies were testing it. They had their own way of how to implement it, which is really just simple sounding, but it was per their protocol they established. So all these radios that were made were just not interoperable with each other. Think back to the early days of cellular technology. Everybody was trying to figure out which would work, and in the end, a lot more people bought on board with this kind of worldwide standard. But even in the 80s and 90s and 2000s, there was different types of cellular technology out there that were not interoperable with each other. So in 1986-ish, around that time frame, second generation automatic link establishment was finally adopted and put together through a standard. The MIL standard 188, that time 141 alpha was the initial one. And again, the cooperative efforts of several manufacturers put together and the U.S. government. This is what supported non-governmental organizations, NGOs, other agencies within the U.S. government and other governments to be able to take advantage of automatic link establishment. It would begin to increase in usage as a lot of this radio technology eventually became more cost effective. Now in 1998 and around 1999, third generation automatic link establishment was finally adopted, and that was due to significant interest in HF during the later 80s and 90s, in which people were trying to research faster ALE methods. Second generation ALE is slow for link up. It can take 10 seconds or more in order to link up. With third generation automatic link establishment, they used faster methods in order to link up faster, and some other little bits and pieces that they added on. This overall improved capability and performance was realized in MIL standard 188.141b. It does retain backwards compatibility with 2G ALE, it's just that you revert back to 2G ALE. It's also adopted in NATO STANAG 4538, so that our NATO partners can implement what is essentially just the same standard for their radios as well. 3G is not as, I'm not going to use the word popular, but not as widespread as 2G is, mainly because 3G requires more complex system processing and also GPS timing as well involved for it. So you'll find 2G in more widespread usage due to the increased interoperability between different organizations that all commonly would have 2G. But sometimes you'll have these radios that also have 3G as well. So let's look at the technical characteristics behind second generation. Off to your right, you see a waterfall display. Within what we have is a typical narrowband HF single sideband 3 kilohertz bandwidth signal. Within that, you actually see within those boundaries around a 2 kilohertz bandwidth 2G waveform, and it is made up of what we call 8-area frequency shift keying, 8FSK, or also just called multi-frequency shift keying. Uses 8 orthogonal tones found between 750 and 2500 hertz. You can see those clearly visible to your right. Each tone is 8 milliseconds long, and that allows you to transmit the symbol rate of 125 baud, which is also known as 125 symbols per second, which further actually breaks down to the raw data rate of 375 bits per second. Okay, we're not talking about broadband speeds that you may be used to over the internet. Okay, it just is not supportable within this finite amount of bandwidth. The ALE data itself is broken into 24-bit frames, and of those 24 bits, there's a 3-bit preamble followed by 3 ASCII characters. In this case, it is making each of these ASCII characters out of 7 bits each. This is for the very basic second generation ALE standard. They, in future standards between second generation and even third generation, increased the amount of bits used in these frames. And instead of ASCII characters, went to representing the information in just straight binary. Okay. So then you're transmitting this. That means the radio on the other end has to have the ability to process that signal and decode it, and then be able to then pull out the ASCII characters and the rest of the ALE data. The great thing about digital communications, again, I will explain more in the next episode, but the great thing about digital communications is you're able to communicate at a much lower signal to noise ratio than you could with normal voice, because the voice may be unintelligible at the other end, whereas with digital communications and with these increased digital signal processing techniques, you can pull this data right out of the noise. And so you're able to achieve negative decibel signal to noise ratio ratings and still be able to communicate. So if you're out there in the field and you're not able to hear the other person that well, you can barely make them out. If you were just using ALE and other digital communications techniques, you're able to actually pass the word through, with whether it's with digitized voice or with actual just text data being sent back and forth. You're still able to make the most out of HF communications, and this is where the magic really is with HF, and the ability to utilize and leverage digital communications to achieve communications where you couldn't otherwise if you were using just straight analog voice. Okay, so where is this used? U.S. Army Mars uses 2G ALE amongst all of the volunteer hams that are accredited to operate in the military auxiliary radio system. We have interorganization, non-government organization, multinational partners. A whole suite of people are using 2G ALE. And I'm not going to forget about you all, amateur radio operators are using this. In fact, HF Link is the, if you want to call them, the organization, also the software that allows you to, through your computer, implement 2G ALE by hooking up any amateur radio that doesn't have built-in 2G ALE capability and be able to utilize it. And then you can not only do sounding to find out which frequency is the best to use for a specific station, you're also able to include short text messages within this protocol and be able to pass information where you might not have been able to if the analog voice was too weak to make out. So on to third generation automatic link establishment. In this standard, unlike 2G ALE, 2G ALE is asynchronous. In this case, 3G ALE is synchronous, in which all of the radios are timed such that they're all looking at the same block of time to pass a message or to receive a message. Unlike 2G ALE, where everybody's just blindly going through all the channels not synced. And so eventually they're going to tie and link into each other as they're all testing each channel, or on the receive side, they're receiving on every channel and flipping through, and eventually they link up. Whereas with 3G ALE, it's intended that they're all going to be transmitting or receiving and listening to each other at the same time, or attempt to. So that requires GPS, and it requires some way to ensure that everybody's got the same time. Typically in a 3G ALE network, we set up a time of day server to ensure that you have a station that can establish what is the correct synchronized time. We also have additional language within 3G ALE and definitions. We have dwell groups, we have limited call signs, we have shorter burst transmissions, and that allows for more rapid intervals of scanning. You can typically add more stations to a 3G ALE net. They're not unlimited. Some people have been employing 3G ALE nets that have only up to 50 IDs, users, and with 2G ALE maybe just 30. Or it could be a limitation of just how that radio is allowing you to input that information. So just by looking at the waterfall and also listening, it is much different than 2G ALE. And it actually increases the robustness of what the channel conditions it can work in, because it's employing more advanced forward error correction techniques, and it has a much different way of transmitting the information. It can also transmit the information much faster.